let's go ahead and get started. For the last time, I'll remind you all that you can ask questions at any time, strictly by typing your questions in at the GoToWebinar control panel under the questions section. Okay, let's go ahead and get started. Okay, let's take a look at our agenda today. Today is a complete review of high-speed counting capabilities at Horner. We're going to talk a little bit about some of the applications that require high-speed counting and the different ways you can use the functionality built into the products. Some of the common terms that we use when we talk high-speed counting. Want to make sure we're talking the same language here. There are lots of different modes because high-speed counting means different things for different applications. So we're going to cover the different modes that are supported by our products, what they mean. We'll have examples for most of them. And then at the end, we're going to do a comparison between the different Horner product lines and what the high-speed counting capabilities are from series to series. So that'll be what we cover just before the question and answer session at the end. All right, let's get started talking high-speed counting. Okay, so I wanted to share just a few example applications for high-speed counting. And again, it means different things for different machines. One very common requirement for high-speed counting functionality is the requirement that you need to keep track of machine position. You know, maybe you have a stamping press, which has a 360-degree cycle from bottom dead center to the top of stroke. And you need to keep track where you are in that cycle. Very commonly, an encoder can be used for that sort of application on many different types of machines, using something called quadrature mode very often, so that we can get that position information into the controller in real time without losing a beat. Another application, which is very common, is a requirement to count things on a production line. Maybe you're counting bottles as they fly by in a bottling application. Maybe you're counting pieces of paper for an application. Some sort of output from a sensor, a photo eye, something like that. And in that case, you're going to be using something we call totalizer mode, and we'll go through that in a bit. Another application might be where you're cutting a product to length. So you're going to feed out a certain length of product, maybe using encoder to verify that you've fed out the right amount. And then very precisely at a certain position, you're going to, fire a knife or some sort of automated cutter to make sure you get that length exactly right. So that's another common application. Another one is measuring flow rate for a process application. Maybe there's some sort of fluid, maybe it's water. You want to know the number of gallons per minute or liters per second that is flowing in the application. You might use a flow rate sensor that has a paddle wheel built into it that's putting out pulses. And by monitoring and measuring frequency, you will know what the flow rate is. So there's 4 different examples of quite different high-speed counting type applications. The next thing I want to talk about just briefly is, the approach that Horner takes in implementing high-speed counting. And we've been doing this for many years. The very first version of the OCS controller many years ago used this approach, and it's served us well and provided a lot of power and flexibility and performance. So what we do is we utilize a special piece of silicon, a component called either an FPGA or a CPLD, for instance. And this is a dedicated part that handles all the high-speed input and high-speed output requirements for the application. So it does not require that time-critical signals be dependent on the logic scan in order to perform their function of counting or timing an output, whatever the case may be. So those high-speed input signals are wired directly into the gate array chip. The high-speed output signals, similarly, are also wired directly into the gate array chip. And then using Cscape, we configure the mode of counting that we're going to be doing, because as we've already mentioned, there's lots of different ways that you need to do counting in a typical application. Those 4 high-speed inputs can be flexibly configured, again, depending on the application and what you need them to do. And then you have a bank of assignable registers, real-world I/O type registers that are assigned to the high-speed counting function that you can then use for, the non-time critical functions, reading the value in the accumulator, how many counts or the time that you've accumulated, whatever the case may be. So this approach of using dedicated silicon means very strong performance with high frequencies supported and a lot of flexibility in the functionality of the function for the machine. Okay, before we dive into the different modes and how to configure them and those sorts of examples, let's just spend a couple minutes talking about some common terms that I'm going to throw about here. And I want to make sure you understand what we're talking about. Many of you, I'm sure, do as experienced controls engineers, but not everyone does. Totalizing is one term I'll mention. That's just really a fancy term for maintaining a count or a sum. We often call counting totalizing. The accumulator, well, that's a special register where the current count or sum is stored. We use that same term when we talk about timers and counters in logic, but in this case, we're talking about a special accumulator where the high-speed counter information is stored, where we can retrieve it and where we know that value is accurate regardless of scan. And then we have four terms that are really different functions that, depending on the high-speed counter mode, we may need to perform using either the high-speed inputs or maybe internal functions if they're not super speed critical. And these four functions, I'll go through these. First one is disable. You don't always want to count all the time. You often only want to count during certain machine conditions, and a disable signal, whether it's an internal bit for a non-time critical scenario, or an external high-speed input, if it is time critical, that external disable or internal disable signal will prevent the counter from counting when you don't want it to. Also, we've got a couple more terms, clear and preload, which are very similar. A clear function effectively sets the accumulator to 0 as long as it's active. And a preload function does just about the same thing, except that the value doesn't always have to be 0. So you may want to preload a value of 100 instead of 0. So in that case, instead of using a clear, you could use a preload. And flexibly, you can actually do a preload of a value of 0 and skip the clear altogether. And the last one that can be useful from a function standpoint is a latch. So very often we might have a free running counter that's counting time ticks or something like that. And when a very exact type scenario hits, a certain signal turns on, we want to latch the value in the accumulator and then access it on the next scan with whatever the value was at that instant. So a latch function, which is sometimes called a strobe function, is another term that we'll be talking about. And then lastly, I want to talk about edge sensitive signals or level sensitive signals. So with edge sensitive signals, a function such as, let's say, a clear function will be active anytime the signal changes, say, from 0 to 1 with a rising edge or 1 to 0 with a falling edge. Okay, so if your function that you're configuring, you only want the trigger to occur on either the rising edge of the pulse or the falling edge of the pulse, then you would configure an edge sensitive configuration for that function. A level sensitive configuration means that that function will be active the entire time the signal is on or off, depending on how you've configured it. So it doesn't care necessarily about the leading or falling edge. It cares about whether the signal is a 1 or a 0. So those are important things to keep in mind when you're configuring the high-speed counter to get the results that you want. Okay, now let's talk about all the different high-speed counter modes that we support in the Horner OCS product lines. Okay, so to kind of summarize them here, we have a series of totalizing modes. We'll go through these individually. We have the ability to do frequency measurement, where we're measuring the frequency in hertz for a particular pulse train. We have pulse width measurement, where we're measuring the width of the on or the off pulse. We have period measurement, where we're measuring the entire cycle on plus off to report the period, which is reported typically in time and not frequency. And then we have quadrature mode, which is that special mode we use when we're interfacing typically with an incremental encoder for position, whether that's linear position or rotary position. So these are the different counting modes that are supported in our products, and I'm going to go through those individually with examples to show you how you might set those up. Okay, let's talk about the two different categories, if you will, of totalizing modes. One mode of totalizing is where you're actually counting time ticks, okay? So what you're ultimately doing is counting an elapsed time, maybe the elapsed time between one signal and another, whatever the case may be. So that's a type of totalizing, again, where you're counting time increments. So we'll give you an example of that. The rest of the totalizing options are all about counting events, whether it's a rising edge signal or a pulse or whatever the case may be. And we may want to count up all the time. We may want to count down all the time. We may want to count up and down. So one input signal is going to cause our accumulator to increment, and another input signal is going to cause our accumulator to decrement. Or we may have a slight variation on the up down, and that is clock and direction, where we're going to count every time the first input is on, but whether we count up or down is going to be determined by the state of the second input. So those are all different event counting totalizing options. Let's start looking at some examples. Okay, let's start with an event count, okay, counting the number of products. You know, it could be a whole variety of things. It could be, again, bottles on a bottling line. It could be counting pieces of paper, whatever the case may be. Okay, so in this example, what I'm doing is I'm configuring two of the high-speed inputs for this function, where I'm going to count the number of products in my machine. Okay, in this particular case, I've configured the real-world high-speed counter input number 1 to count up. So if you take a look at the screenshot on the right there, that is a Cscape configuration screenshot, and you can see that I'm in totalizer mode, okay, and that I'm counting up, all right, and the input for my up count is external input number 1. All right, so what that's going to do is tell me, all right, I'm going to be counting when input 1 transitions from off to on. Now, in this application, I've configured it such that I don't always want to count. So I have allocated input number 2, real-world input number 2, as an external signal that will disable the counter when it's high. Okay, so I will only count whenever the disable signal is not asserted or low, and I get pulses coming in to my first input. Now, at some point, I'm going to want to clear the accumulator. But in my application example here, that is not a time critical function. So I'm just assigning an internal real world IO bit or a Q bit as the clear function, and I will turn that Q bit on in my logic to execute the clear. Because in my application example, if that happens over a period of a few scans, that would be fine. It doesn't have to happen at a precise instant in time. Okay, and then my accumulator is going to contain the product count. But keep in mind, it's only going to be counting whenever the disable signal is low and my clear function is not asserted in logic. Because if my clear function is asserted in logic, I'm just going to be sitting there with a value of 0 in my accumulator. So this is a very common application. And again, the things that vary from application to application are how time critical is your clear? Do you need a disable or not? I mean, if you're always going to count pulses, regardless of the machine situation, you don't need a disable function in the particular application, but it's available there if you need it. Now, one question people often have is, all right, I know that I need to look at the accumulator for my values in this example, for instance, but where is the accumulator accessed? Well, there is a whole set of I, Q, AI, and AQ registers that are assigned to the high-speed counter. Those can be moved around, but the defaults are shown in these tables here. Okay, so for my example, I need to look at the accumulator, and that's an AI 401 as a double integer. It's a 32-bit accumulator. And my clear function that I'm going to perform in logic is Q1603. So by turning that coil on, I will clear my counter. So again, in the high-speed counter chapter, in the user's manual for every product we sell, you will find all the details on the default memory map for the high-speed counter function. Okay, let's move on to the next example. So our last example, we were effectively counting an event, a number of products on our machine. Now what we're going to do is we're actually going to count time between two inputs in this next application. So again, we're counting time ticks, not necessarily strictly counting the inputs. So how can we set this up? You see the diagram on the lower section there, where I'm showing you what the signals look like. I've got two inputs. I've got a pulse that comes in on input number 1, another pulse that comes in on input number 2, and what I'm interested in is the elapsed time between the leading edge of both pulses. Okay, so how might I set that up? Well, one way I can set that up is, again, utilizing totalizer mode, and you can see the snapshot from the high-speed counter configuration for the totalizer mode. But this time, it's configured for internal, okay, and it's configured to be counting internal clock ticks at a 1 megahertz rate. Okay, so that's what we're counting. We're not counting something external. We're effectively counting internal clock ticks. So by manipulating our clear function and our latch function, we can ultimately end up with the elapsed time in 1 microsecond increments in our latch register and get the value we're looking for. So again, to review the configuration there, we start out by saying that our first real-world input, which is the first pulse, it's going to clear the counter on its rising edge. Okay, so we've configured that clear function, again, going back to the Cscape snapshot, we've configured the clear function for external input number 1 and as a rising edge type clear. Okay, now what that means is that the accumulator will start from 0 when after the clear is complete, and it will start counting 1 microsecond clock ticks, and those will just keep accumulating in the accumulator. And that will continue to occur until the second input turns on, because the second input is configured as a latch and also as a rising edge. So as soon as that second input goes high, then we will latch the value in the accumulator, which will happen to be the number of 1 microsecond clock ticks since our first pulse went high. And then when we do a latch, what happens is we copy the current value of the accumulator into a second register called a latch register, and that way it'll be frozen in time while the accumulator will continue to increment with values beyond what we want to measure. Okay, so where do I find the latch value? Well, the latch value is the double word register right after the accumulator for each counter. Okay, and the examples I'm using today, I'm using an XL4 high-speed counter as the specific examples. All right, now let's move to some simpler applications or simpler setups. Let's talk about frequency counting. Now with frequency counting, okay, so instead of selecting totalizer as your type, you effectively select frequency counter. Once again, the Cscape snapshot is on the right there. Now you have 4 options as to how often you want to calculate frequency, or how often you want the OCS high-speed counting function to calculate frequency. You can calculate every second, every 100 milliseconds, every 10 milliseconds, and every millisecond. Now keep in mind, the faster you recalculate, the lower your accuracy and narrower your frequency range will be. You want to make that update option the widest one that you can live with for the application. That'll give you the best results. If you have a relatively slow moving application, you don't want to be over calculating your frequency and having instability that you don't really need. Okay, so that's the setup there. Select frequency and you select your update rate. Now our example here is where we have liquid flow through a paddle style flow meter, not a flow meet. My graphic is covering up the flow meter word there. And I've just configured it very simply, whereas input number 1 is set for frequency mode and 1 second updates. And in this particular case, I'm not configuring anything for disable or latch. I'm just allowing the frequency to be updated in the accumulator once per second because that's how I've configured it. And I'll be able to take that frequency, and in my logic, I'll be able to take that frequency and then using a conversion factor based on whatever is in the documentation for the flow meter, convert that frequency into a liquid flow. Okay, so that's a pretty simple example for frequency counting. Here's a couple other modes, or one specifically we'll go to next, and that is to accurately measure the width of the pulse, okay? And you have your choice to measure the width of the pulse when it's high or measure the width of the pulse when it's low. All right, so in my example here, we're going to measure the width of the pulse when it's on or high, okay? We're wiring the signal to be measured as high-speed counter input 1. So you can see there, I've configured pulse width management, or measurement, I should say, for my type. And I'm caring about the width when it's high, and my results are going to be in 1 microsecond counts. It's connected electrically to the external input, number 1. Okay. And then effectively the accumulator, as pulses come in, the accumulator is going to be displaying the width of the last pulse in 1 microsecond increments. And again, the accumulator is continuously updated as new pulses come in. Okay. A very similar approach, but a slightly different mode, is called measuring the total period of a pulse. So this time, instead of just measuring when the pulse is on or off, we're going to measure the entire on-off cycle, or the period of the signal. Okay, but it's very similar otherwise. We set it for period measurement. In this case, we want we're going to start measuring the period from the rising edge. We could decide to start measuring the period from the falling edge, okay, or the trailing edge. We could decide that. But instead, in this case, I've configured it to measure starting from the rising edge. And then again, as pulses come in, the accumulator is continuously updated, or I'm sorry, as cycles come in, not just pulses, because it's an on and off part of the cycle. And as those cycles come in, the period in microseconds is going to be reported by the accumulator. Again, a simple application there. All right, now let's talk a little bit about quadrature. So many of you, I'm sure, have used quadrature. That's a special mode when you're using incremental encoders. That's the most common device that uses quadrature. With quadrature, effectively, a quadrature encoder or incremental type encoder typically has 2 outputs. It has an A pulse and a B pulse. And from that A pulse and B pulse, and those pulses are intentionally configured so that they are 90 degrees out of phase. Okay, you can see that from my diagram in the lower right there. Okay, so the A pulse, which I've wired to input 1, and the B pulse, which I've wired to input 2, are 90 degrees out of phase. So by monitoring those 2 signals, the high-speed counter effectively will count up when A is leading B, or input 1 is leading input 2 in this case, and the counter will be counting down when the opposite is true, when B is leading A. So if the encoder most encoders are rotary, and if it's going clockwise, for instance, it's very possible that A is leading B, and we're counting up. And then when we go the other direction, let's say counterclockwise, it's very possible that B will be leading A, and we'll be counting down. And then in terms of the number of counts, the reason it's called a quadrature is because the counter is counting not just the leading edge of each pulse, but it's counting the leading and the trailing edge of each pulse. So for an encoder that has a rating of, say, 1,000 lines per revolution, we actually get 4,000 counts per revolution. So that's how that rating works. Okay, so our example here, in terms of how we configure it in Cscape, again, we configure under type quadrature. We can select whether we want to count down when 1 is lagging 2, or if we want to count up when 1 is lagging 2. Okay, the most common would be when 1 is lagging 2, we're going to be counting down. But if it's working the opposite way you want, just flip that mode setting to 1, or to 1 lags 2 count up. That's the other option there. Okay. So again, A signal is connected to input 1, the B signal is connected to input 2. Now some encoders have something called a marker signal. And that is something that you can use with the OCS if you choose. If you do, you would, in this case, you would wire it most likely to input number 3, for instance. And what is a marker pulse? Well, a marker pulse is a pulse that's on exactly once per revolution. So it's often used in the find home operation, where you not only want to go to a home switch, for instance, but you want to then line up your marker exactly with the home switch so that you have the most accurate find home possible, for instance. So again, marker is an option you can wire into the OCS high-speed counter option. But in this example, I'm not using the marker. So in this case, I'm just going to use a clear function from an internal bit, an assigned Q. The reason I'm doing that is because I'm probably going to clear the accumulator when I do a find home function or something similar, and that typically is done at low speed. I'm going to find home, get where I want to get, and then, you know, over the course of the next couple scans, I'm going to go ahead and clear the accumulator. So when I start moving again, I'll start counting in the appropriate direction and have an appropriate value for position. And the accumulator contains my current position and counts. So again, that's quadrature mode with high-speed counting. Also, when we're taking a look at where we can find the clear bit, we see the clear bit on Q1603. And again, that information is in the high-speed counter chapter of the user's manual. Okay, so we've effectively reviewed the different modes that are available in the OCS high-speed counting functions. Now let's talk about some of the capabilities of individual product lines in terms of how they support high-speed counting. And there are some variation from product line to product line, but it's actually a lot more consistent than you might otherwise think. Okay, so the products of ours that support high-speed counting include all of the micro series OCS products. As you probably know, but may not, the micro OCS series is the newest series of OCS products. It's designed as our entry-level products, but even though it's entry-level, it does have very good high-speed counting capability. Our XL series OCS is our bread and butter product line. It also does a very good job with high-speed counting. And then one of our newest products from a high-speed counter standpoint is our RCC 6512 programmable high-speed counter coprocessor. So that's a unique product that doesn't just count, but it not only provides a variety of advanced counting functions, and it has a very flexible means of interfacing over a variety of networks, Ethernet, CAN, etc. But it also has some built-in logic capability to do some logic remotely. Now, it's typically used with other OCS products, but doesn't have to be. It's just that the amount of local logic is limited, and we'll talk about those limitations later. So it would have to be a relatively small application for it to be doing all the work in the application, instead of working alongside, for instance, an OCS that is doing the bulk of the machine control. Okay, so those are the 3 products that support high-speed counting. Let's start by taking a look at the micro OCS series. Okay, so even though it's an entry-level product, and the X2, for instance, has a list price of below $240, the X4 is below $400, the X7 is very cost-effective as well. The max frequency that's supported is 500 kilohertz. That's pretty substantial for an entry-level product. Most entry-level products or many of them at least, are down around the 1K, 5K, 10K range. We can handle signals up to 500K. We can also handle up to 4 counters. So depending on the mode, you can have up to 4 accumulators going at any given time. From a modes that are supported, it does not support all the totalization modes. For totalizing, it primarily supports counting up, okay? But it does fully support frequency counting, pulse measurement, period measurement. It can handle up to 2 quadrature encoders, and it can handle up to 2 what we call match outputs. Now, I didn't give you an example specifically of match outputs, but what those are real-world outputs that are wired directly to that FPGA when I showed you the diagram there early in the presentation. And those outputs, instead of just being controlled strictly from ladder, they can be controlled from the high-speed counter chip, such that when a certain count is reached in the accumulator or a certain position is reached in the accumulator, you can automatically fire those outputs independent of scan, which is very powerful. It gives you programmable limit switch type functionality. So in the case of the micro OCS, there are 2 high-speed outputs that can support that mode. However, they strictly turn on based on accumulator value, as opposed to having options such as turning on, turning off, or toggling. But again, the micro OCS series has very powerful high-speed counting capabilities. All right, let's next take a look at the 2 entry-level points to the XL series, and that is the XLE and XLT with Ethernet. It's a little bit of an alliteration nightmare, but it's the XLEE and the XLTE. So these products are updated versions of the classic XLE and XLT, which remains a very high volume product for us. They added built-in Ethernet capability, along with faster processors and upgraded high-speed counters. So now these 2 products, the XLEE and XLTE, support up to 500 kilohertz frequencies. Again, up to 4 counters, which have always been supported, but not nearly at this frequency range. The old frequency for the original XLE and XLT, I believe, was 10K. So vast difference between 10K and 500K, obviously. And its mode support is very similar to the micro series. Supports totalizing, count up only, but it supports everything else: frequency counting, pulse measurement, period measurement, 2 quadratures, and 2 match outputs for turning on an output based on position. So that's the XLE and XLTE, and those again have been updated with some really nice high-speed counting capabilities. Next, we get to our mainstream XL OCS series. Now, these products have more powerful processors than what you'll find on the XLEE and XLTE, even though they're in the same product series. They also are Linux-based from the standpoint of their operating system. Of course, it's a real-time Linux operating system that's not, accessible by users, but that's what it happens to run on the inside. And the XL series has very good frequency support. So it can actually support up to 1 megahertz from a frequency standpoint. 500 kilohertz takes care of almost all applications. 1 megahertz does even better. Now, one thing that's a little bit of a compromise here is because the XL series FPGA chip was designed in several years ago, it supports either 2 highly functional counters, or if you change a file in the firmware and update the firmware, and you can get that file from our tech support group. If you do that update to the FPGA file via firmware, then you can get up to 4 counters. They're just not quite as capable. Okay, they don't have quite as many options. So that you may have to do, if you want to support 4 counters, you will have to load a special version of firmware to do that. But it's not a big deal. We make updating firmware in the field as fairly easy. You can do that from micro SD. You can do it from USB. Okay, so the modes that are supported, all modes are supported. All the examples I did were done with an XL4 in mind. So all the totalizing modes are supported. Frequency counting, pulse measurement, period measurement, 2 quadratures if you're in 2 counter mode. If you're in 4 counter mode, there's no quadrature support, so be aware of that. And then there's also 2 match outputs, but these outputs can either turn on based on position of the accumulator or a value in the accumulator, or turn off or toggle. So they're a little more configurable on the match output side than what you'll find on the micro series and the XLE and XLT. Now, one thing that is not necessarily intuitive is that the X5 has the same internals as the XL family. So yes, it's part of the micro family. It looks like a micro from the standpoint of its package. However, the internals are very similar to an XL series product. So that's why its high-speed counting capabilities are aligned with XL series and not aligned with the micro series. Okay, now let's talk a little bit about filtering before I move on to the RCC high-speed coprocessor. So whenever you're counting pulses or transitions, whatever the case may be. And you have a counter which is capable of reading very fast signals. You definitely have an opportunity for spurious signals that might just be noise to be counted when you don't want them to be counted. So one of the capabilities that we have built into all of the high-speed counter products I've talked about so far is something called digital filtering. And with the digital filtering, you can set it up to effectively eliminate the potential for spurious signals. So generally in most high-speed counter applications, you have a certain frequency in mind or a certain period in mind or pulse width in mind when you set up the application. You know that regardless of what happens in my machine, I'm not going to be getting legitimate pulses in, let's say, that are more frequent than every 5K or more frequent than every 50K. So by understanding the width of legitimate pulses, you can configure our digital filter in the high-speed counter function to accept all those legitimate pulses and signals, but reject the ones that are just maybe short impulses that don't belong. So how do you do that? Well, there's two settings with our filter, and I really think of this filter as an oversampling filter. That's the way I think of it. So the first thing you set up is it's labeled filter frequency on the setup dialog, but I think of it as sampling frequency. So in this case, I've set up my sampling frequency at 20 kilohertz. So that means that on a 20 kilohertz rate, I'm going to be sampling the input, each input of the high-speed counter to check its level. Is it off or is it on? And then the second thing I configure is how many consecutive samples have to match before I'll either pass my on or my off, if I'm already on, for instance, on to the accumulator. So again, what is my sampling frequency? How often am I going to be checking the status of the input? And then how many consecutive samples have to match before that data gets passed through to the accumulator, or that count gets counted, if you will. So that's how we set up our digital filtering. And it's very important for applications that have a lot of noise, where you can get spurious signals that are not the pulse that you're looking for. You want to make sure you've filtered those out. Okay, so the next thing I'm going to talk about, and again, here's all the calculations. So let's go ahead and wrap this up. I've got all the calculations here. So if I set up this digital filter at a sampling frequency of 20 kilohertz, and then I need 4 consecutive samples before I effectively count up or count down or basically pass the signal on. What does that mean? Okay, well, at a sampling frequency of 20 kilohertz, my sampling period is 50 microseconds. So what that means is if I need to have 4 consecutive samples to match, that means the minimum valid pulse I'm going to receive is 200 microseconds wide. All right. And if I want to know what that frequency is, and I'm thinking about like a 50% duty cycle where my pulse is on half the time and off half the time, they're not always that way. Keep that in mind. They're not always that way. But let's say we're assuming a 50% on, 50% off duty cycle. Then we have to take our 200 microsecond pulse width and double it to get our period of 400 microseconds. And when we invert that to get frequency, we come up with 2.5 kilohertz. So what this means is I've configured this frequency, or I've configured this filter to filter out pretty much all the high frequencies above 2.5K. All right, so I won't have to worry about some 75K or 200K spurious pulse coming in and disturbing my my count or my application. All right, next we're going to talk about the RCC high-speed coprocessor. Now this is a really, I hate to use this technical term, but this is a really nifty product where we have effectively taken some pretty advanced high-speed counting hardware and wrapped it around a microprocessor that has logic capability, added some pretty flexible communications networking, including Ethernet and CAN, And we've provided logic capability so that you can program locally in ladder logic for other functions that are not time critical for your high-speed counter requirements. So keep in mind, we still have the FPGA with high-speed inputs wired to it and high-speed outputs wired to it. But now instead of 4 inputs and 2 outputs, with this product, we have 12 inputs, so 12 physical digital inputs and 8 physical digital outputs that are wired to our gate array. And we can support maximum frequencies up to 500 kilohertz, and we can support up to 8 accumulators, so up to 8 counters, depending on the mode. And we support all the modes. So all the totalizing modes, frequency counting, pulse measurement, period measurement, quadrature, and from a quadrature standpoint, we can support 4 quadrature channels. So our other products max out at 2. With this product, we can do up to 4 quadratures. And we can mix and match between quadrature and totalizing, counting events versus counting time ticks, all those sorts of things. Highly configurable. And then we have up to 8 match outputs, which means those are digital outputs which we can fire based on an accumulator value. And that could represent an encoder position, that could represent a certain number of counts, whatever the case may be. And there's some other advanced things we're doing here. One of the advanced things is we have a much more flexible input voltage for the inputs than we have on our standard products. Keep in mind, our standard products most of the time are interfacing with 24-volt signals. Sometimes they're 12-volt signals if it's a mobile application or just a 12-volt battery-operated application, for instance. But this product can support not only 12 volts and 24 volts, it can also directly support 5-volt levels as well as zero crossing 0-volt levels as well. So more flexibility on the inputs from a voltage standpoint. And then instead of digital filtering, this product supports analog filtering. So you have the ability to set up an analog filter at either 500 kilohertz, 50 kilohertz, or 5 kilohertz to effectively knock out completely those spurious noise signals that you don't want. And we've got a very good customer that uses this product in quite a big volume. And they, when they first started using the product in their test cells, they were getting spurious readings, and then they thought, oh no, we have a problem. A quick phone call and a quick check of the user's manual, and they're able to take advantage of the analog filtering and get rid of their problem very simply. So again, filtering is very important when you have a high-speed counter that's got high frequency support. And in the case of this product, we do the filtering in an analog domain, and it does a really good job of it. Okay, and then from a logic standpoint, I mentioned to you before that this unit is programmable in ladder logic, but it is a little bit more limited than most of our products in terms of the amount of logic from a size of the program standpoint, and then the amount of variables that it supports. So you can see there on the screen in the lower right, this product is intended as a coprocessor. So it supports up to 16K of ladder with a more limited number of variables, about 1,800 that are non-retentive and 256 that are retentive. Those are all word types. And then we've got 2K of non-retentive bit types available as well. And if you need retentive bits, keep in mind with our products, you always have bit level access to retentive words. So those will be supported as well. You just go at it a little different way. Okay, so that's the RCC 6512 high-speed coprocessor. Again, it can interface over Ethernet or over CAN back to a standard OCS. It also actually supports serial communications as well. You could even communicate over Modbus if you needed to. And it's configurable from Cscape, and it uses a USB port for the most common Cscape configuration method, although you can configure it over Ethernet, you can configure it over CAN, you can configure it over the serial port. All those are possible. Okay, so that's the RCC 6512 high-speed coprocessor. Now, I don't have it on the screen here, but I will mention from an Ethernet standpoint, it supports Modbus TCP as a master or slave. It supports Ethernet IP as an I/O device. It also supports FTP file transfers. It also supports, I believe, email. So you could use this product to generate email alarms and those sorts of things. So it's still very functional, even though it doesn't have all the logic space as well as all the protocol support of every OCS. And then from a CAN standpoint, it supports our standard C-scan protocol, and you can potentially, you know, have it communicate to other OCSs over C-scan, or even potentially add some I/O over C-scan. All right, now let's take a look at a chart, because we always got to have charts, right? So here you can kind of see at a glance what the high-speed counting capability is of our products. I've kind of highlighted the areas where there's some differentiation, reminding folks that the XL series, while it has a very powerful high-speed counter built in 2-counter mode, it only supports a total of 2 counters. If you need 4 counters, you just need to make a firmware change or a firmware update. And then the RCC 6512, I've highlighted the fact that it can support a total of 8 counters, that it has analog filtering instead of digital filtering, and that it has 8 match outputs. And I probably should have also highlighted the fact that it supports up to 4 quadrature inputs as well. So, because that's definitely a differentiator. So for pure high-speed counting capability, the RCC 6512 is really advanced. Okay, before we dive into questions, I want to just refresh our June webinar schedule. For those of you who missed the webinar last week, the recording is up on our website at hornerautomation.com under resources and videos. Today's webinar will also, the recording for that will also be posted shortly, certainly by the end of the week. And then next week, we have our Seascape 9.9 Service Pack 3 walkthrough. So we've talked about different pieces of Service Pack 3 from the standpoint of tag-based logic and MQTT push-style communications. We're going to kind of walk through the software in general. We've managed to implement several of the suggestions and feedback that we got from our beta testers, and we're excited about that. So we've got some more things we've rolled into it for usability purposes, etc. So I'll be introducing that next week. Okay, now we're to the questions and answers. Let me see if I can find my mouse. There we go. So I can see the questions. All right, and once again, I'll remind you that you have the ability to continue to ask questions while we're wrapping up the session in the GoToMeeting questions area. Okay, so very good question. Where is the counting configuration menu access in Seascape? So that's done through the hardware configuration. So you would go to the hardware configuration, which is accessible from multiple places in Seascape. And there you would configure your controller. So let's say an XL4, for instance, maybe a Model 3 that has 12 digital ins and 12 digital outs. That's just one example. And then you would go to the local I/O tab, and under the digital input configuration for the local I/O tab, that's where you'll find all your input configuration, including the high-speed counter capabilities. What's the trigger level for edge detection? I'm assuming, well, basically those would just be the on levels and off levels. So, for instance, you know, we talked about the fact that well, let me back up a little bit. Okay, we're talking edge detection, not level detection. So for a rising edge, okay, we're looking for as soon as a signal reaches the voltage turn-on threshold for the input, for the high-speed input, that's the point at which it's going to be turned on logically. So let's say I have a 24-volt input wired into my XL4 high-speed output number 1. And it's a 24-volt signal, and on the top of my head, I don't remember, but let's say that our on threshold is 8 volts, okay? As soon as we see 8 volts on that input, we're gonna transition that input to an on for counting purposes. Now, the exception there would be if we're utilizing the digital filtering, because with digital filtering, there's a bit of a trade-off. With digital filtering, we're trading between only accepting the pulses and signals that, you know, we've identified as being of the appropriate you know, specifications, so they're not just spurious noise, but that does cause a slight delay in the input turning on. But that's, you know, it's going to be a consistent shift, so it shouldn't impact accuracy. It just might slightly impact when those values come into the accumulator. But that'll all be synchronized on the next scan. So that's generally not an issue Okay, here's the next question. How can I achieve the maximum capacity of 1 megahertz to have quadrature through an encoder? I clarified that my OCS XL7 already supports up to said speed. Okay, well, it's partly going to be dependent on your encoder, whatever the maximum frequency is that your encoder can support. So you're going to have to purchase an encoder which has a maximum output that can go that fast, because they aren't all made to go that fast, and they don't always necessarily. The other factor is not only how fast they can rotate, but also how many, effectively, how many lines per revolution are occurring, how many transitions on the A pulse and the B pulse are occurring per revolution. So it's a matter of having an encoder that's rated properly to be able to get that sort of frequency out. I think I'm answering that question the way you want it. Will the counters work at 5 volt levels, or do all inputs work at greater than 12 volts? So if you have a 5 volt requirement, the RCC 6512 programmable coprocessor supports 5 volt levels, whereas the remainder of our products do not. They only support 12 volt and 24 volt levels. And again, I believe the threshold is about 8 volts on those. So that's really what you're looking at there. Now, a couple things I will mention. I'm not a young guy, so I've been in this industry for 30 years or so. So it's far, far easier today to find 24 volt level encoders, for instance, than it was when my career started 30 years ago. So they're a pretty common option to be able to select a 24 volt voltage level. Okay, next question. Can the digital filtering be changed on the fly based on machine speed? I don't believe it's designed to do that, no. So it's certainly not, keep in mind, these are settings in the FPGA chip, okay? So the settings for sampling frequency, as well as the number of consecutive samples that I need to have in order to, filter out the spurious noise that I don't want in my system, those are settings that I'm sending off to the FPGA chip, and those settings are not done at runtime. So no, those are done in configuration. I don't believe we have the option of even enhancing that in the future given the current architecture, but I will check. Does high-speed counting / IO filtering affect quadrature mode? Sure, it does. But again, it should not adversely affect it. It would just slightly delay it, depending on what your input filter is. But even that delay is going to be consistent across the board, so it's not going to negatively impact your quadrature mode. It will probably positively impact your quadrature mode by getting rid again of spurious noise that you may be experiencing. Let's see. You mentioned the Q clear bit is for non-sensitive clearing. What is the best way for clearing a totalizer if it is time sensitive? Well, that would be from an external input. So you would effectively configure your clear input, and the same argument can be used for preload as well as disable, etc. For those that are super time sensitive, you're going to want those to come in through an external physical input, because those physical inputs are wired directly into the high-speed FPGA chip and are not impacted by logic scan. So yeah, so in that scenario, you're going to want to use some sort of external signal that you can wire in that way. Okay, so one thing, I had a suggestion from an experienced user who reminded me that if you're going to use 4 counter mode in an XL series OCS, like an XL4, for instance, or an XL7, that once you update the firmware, that there is a little work on the Seascape side to make sure that your Seascape configuration matches the 4 counter mode that the OCS is now configured for. So if you don't, there will be a mismatch between what Seascape is expecting, 2 counters, and what the OCS is configured for, 4 counters. So there's just a little bit of configuration that has to change there in the hardware configuration. Will I have a stepper output control webinar in the future? Yes, we will cover our high-speed outputs in much more detail in a future webinar, absolutely. So that includes, from a high-speed output functionality, we're talking about the ability to output a fixed frequency or a variable frequency. So you might have an output that, let's say you're going to vary the frequency. You may have another application where you want to keep the frequency constant but vary the duty cycle. You may have another application where you're trying to do some sort of positioning, like some sort of trapezoidal move profile with a stepper indexer or something, or a stepper motor drive, for instance. So those are all high-speed output capabilities that most of our products can handle. So I'll be covering that in a future webinar. Let's see, what PWM options for the outputs does the coprocessor have? Good question. I believe it only supports match. I don't think we have added yet support for 8 PWM channels or 8 frequency channels or 8 stepper outputs. I'm certain on the stepper side we haven't, and I'm pretty sure we haven't added those other ones either. So today the 8 outputs are primarily for match, so that when the accumulator reaches a certain count, that could be again from an encoder or from just counting from totalizing, you're going to fire that output independent of the logic scan. What is the maximum frequency of a normal digital input? A normal digital inputs are scan dependent. Okay, so it depends on the scan rate of your controller. Every digital input is scanned every scan of the controller. So if your scan rate is 5 milliseconds, that means that best case scenario, absolute best case scenario, and it's actually less than this, is absolute best case scenario is you could see potentially, around 100 or 200 transitions per second. But anything like that, you're going to want to use a high-speed counter for. So in general, your digital inputs are scan dependent and your high-speed inputs are not. That's the key thing there. Okay, I think I've reached the bottom of our questions. Had a lot of good questions today, and I appreciate, again, the fine attendance and the fine questions. So as a reminder, a week from today, I'm going to be doing a walkthrough on Seascape 9.9 Service Pack 3. And for those of you who want to reference this material later, to come back to it, you can always go to our website at hornerautomation.com, go to the resources section in the video page, and you'll find all of our past webinar recordings along with a variety of other videos that hopefully are useful to you as you plan your applications. Everybody have a great day and stay safe.